In this video, we will look at some of the ways that climate change will affect water utilities. As we've said, climate change is a component of the dynamic baseline, just like economic growth and demographic changes. Policy interventions to address water and sanitation problems in developing countries will occur in a world in which the effects of climate change are unfolding. Climate change will have a multitude of effects on efforts to address water and sanitation problems in developing countries. In this video, we'll focus on climate change and water utilities. Climate change will also affect rural and community water supply and sanitation projects, but unfortunately we don't have time in this course to discuss that topic in detail. There are four big consequences of climate change, all of which will impact water utilities. First, precipitation is likely to change. In a particular locality or city, it is often highly uncertain, though, whether average rainfall will go up or down. Some water utilities are likely to face reduced raw water supplies. Second, temperatures will rise. The direction of this effect is very certain. Third, extreme events will increase. Increased weather volatility is also very likely. Many water utilities will therefore have to deal with more violent storms and increased droughts. Even if average rainfall stays the same, increased volatility will impose increased costs on utilities. Fourth, the sea level is rising. The magnitude of sea level rise is uncertain, but the direction of the effect is not. These four effects of climate change will affect water utilities through both supply and demand side linkages. For example, consider the consequences for a water utility if rainfall declines. On the supply side, the utility's raw water sources decrease. The yield of water supply reservoirs also declines. On the demand side, decreased rainfall means that households demand more water to irrigate gardens and for landscaping that used to be irrigated by rainfall. So demands on the utility are going up as supplies are going down. Next, consider the effects of increased temperature. As temperatures rise, evaporation losses increase from a utility's water supply reservoir, decreasing yield. But at the same time, household water demand increases as temperature increases. More water is needed for cooling, bathing, and plants. For cities near the coast, sea level rise may also affect both the supply and the demand side of a utility's operations. On the supply side, sea level rise may threaten a utility's raw water sources, such as water supply wells and other capital assets. On the demand side, the assets of the utility's customers may be at risk, threatening their financial position and ability to pay for services. Extreme events such as typhoons and floods both threaten a utility's capital assets and the assets of its customers. We will next discuss the supply side effects in a little more detail, after which we'll turn to the demand side effects. Water resources planners have always had to grapple with uncertain hydrology. This slide shows the flows of the Nile River from 1871 to 1999. You'll see that there were sequences of low and high years that made managing the Nile especially challenging for planners. They tackled these challenges by making assumptions about the mean and variance of flows, and the autocorrelation between years. They effectively assumed that the statistical properties of the stochastic flows would continue into the future. This assumption is termed stationarity. Climate change has made this stationarity assumption untenable. In other words, it is not safe to assume that the statistical properties of past flows will continue into the future. In their paper shown on this slide, Milley et al. Discuss the implications for water management. Their bottom line is that future hydrology is much more uncertain, and, as a result, water resources planning has become much more complicated. As an example of the effects of non-stationarity on water utility planning, consider the effect of extreme events like floods and typhoons. Utilities have always had to plan for extreme events. This is not new. Utilities have always needed to spend money to protect their capital assets against extreme weather events. What's changed is that utilities find it much more difficult to determine margins of safety for protecting infrastructure against storms. Finding funding to pay for these increased costs is especially difficult for utilities in developing countries, which are often in a precarious financial condition already, even in the absence of climate change. A second effect of climate change on the supply side of water utility operations is on surface water quality. This occurs for several reasons. First, increased extreme events result in larger volumes of runoff to treat, with increased nutrient loadings. Peak loadings are more expensive to handle. A water utility will require more treatment capacity. Second, increased temperature may reduce surface water quality, e.g. algal blooms. Third, low stream flows during droughts of increased duration reduce surface water. A decline in surface water quality increases a utility's raw water intake treatment costs. And on the wastewater side, the utility's treatment costs may increase in order to maintain a given level of surface water quality for environmental or recreational objectives. A third effect of climate change on the supply side of water utility operations is sea level rise. Sea level rise poses threats to both cities and urban infrastructure, such as water treatment plants and wastewater treatment facilities. Wastewater treatment plants are often located near the coast, as are desalination plants. Many of the largest cities around the world are located on or near the coast, where they are vulnerable to both sea level rise and extreme weather events such as typhoons. As shown on this slide, this is especially true in Asia, where large and growing urban populations are concentrated near the coast. The megacities of Bangkok, Jakarta, Manila, Dhaka, Yangon, Kolkata, Mumbai, Karachi and Shanghai all face the hazards of sea level rise and extreme weather events. Sea level rise may also cause catastrophic changes for cities in low-lying river deltas. The next 7 slides show that the land would be inundated in the Nile Delta in Egypt if the sea level were to increase by 1 to 5 meters from present levels. So here we have a satellite view of the Nile Delta, and this is it with a 1 meter sea level rise. Now 2 meters, 3 meters, 4 meters, and finally 5 meters. A 5 meter sea level rise would make the city of Alexandria and much of the Nile Delta uninhabitable for the majority of the current population. As sea levels rise, water utilities are among the most vulnerable infrastructure assets, as both their operations and customer base become increasingly at risk. A 5 meter sea level rise is much larger than most projections of gradual sea level rise, and would of course be catastrophic for many low-lying coastal regions around the world, but it is not out of the realm of plausible scenarios. Climate change has many effects on the customers of water utilities. In the previous video we discussed some of the public health consequences of climate change. One of the most certain effects of climate change on household demand for water services provided by a utility is the direct effect of higher temperatures on household water use. In week 4 we noted that temperature was one of the independent variables in a traditional water demand equation. That climate change will lead to increased ambient temperatures is highly likely. It is also extremely likely that increases in temperature will lead to increases in household water use. This figure shows the pattern of both temperature and rainfall in Egypt. As illustrated, in the summer temperatures rise and rainfall is low. This slide shows the monthly water production and maximum monthly temperature for a large water utility in the Egyptian Delta. The utility's water production is closely associated with maximum monthly temperature. Such peaks in monthly water use are costly for a water utility because it must build capacity to meet the summer peak, and this capacity will then be idle for much of the year. So, climate change causes multiple changes on both the supply and demand side of utility operations. The analytical challenge that utilities face is how to tackle all these changes simultaneously. Water utilities do not have the luxury of tackling all these climate change linkages one at a time. The complexity arises because all of these effects are unfolding at the same time. One example of the increased operational complexity that utilities face is the water-energy nexus. In 2009, cities in Venezuela, Ecuador, Colombia and Paraguay were forced to ration water and cut electricity generation because of shortfalls in surface water runoff from the Andes. In other words, the changes in hydrology caused a simultaneous loss of water supply and hydropower. At the same time, in such situations, increased temperatures may compound management challenges by reducing labour productivity. Operational complexity typically translates directly into financial complexity. Many inefficient, underfunded public utilities have not handled their existing responsibilities well. Now they are facing new challenges without new resources, either financial or managerial. The effects of climate change will make it necessary for many utilities to diversify their raw water sources and to spend money to protect their existing capital assets from extreme weather events. Many water utilities will not be able to finance the development of new alternative water supplies. Cost estimates for the water and wastewater utilities in the United States of America to adapt to the effects of climate change through to 2050 are on the order of $500 billion to $1 trillion US. That's approximately $10,000 US per household over the roughly 40-year planning horizon, or about $50 US per household per month. These costs would approximately double the current average water bill of a household in the United States. But who should pay these costs? Central government or utility customers? And if these costs look expensive for households in the United States, what about for households in developing countries? Most water utilities in developing countries are already effectively bankrupt. John Maynard Keynes said that the real value of cash or liquidity is to deal with uncertainty. But cash is one thing few water utilities in low-income countries have. As a result, they're in a very weak position to deal with the uncertainties created by climate change. In addition to operational and financial complexity, climate change is also likely to increase the regulatory uncertainty that water utilities face. Many regulations have been set in the past without taking into account the effects of climate change. For example, cooling requirements for treated wastewater effluent have typically been established without thinking about the increase in ambient temperatures that climate change will cause. In the last part of this video, we want to give you insight into the kinds of financial instruments that are now being discussed to help water utilities adapt to the complexities created by climate change. As we've discussed, climate change may both reduce a water utility's raw water supplies and increase household demand. As a result, the utility may need to either draw upon additional supplies during drought years or to reduce municipal demand. One way for a utility to tackle this problem is to couple an options contract with a reservoir insurance policy. I'll first explain how the options contract would work. The water utility pays for the right to buy water from farmers at a specified price. The water utility does not have to exercise the option, nor does it plan to exercise the option during periods of normal rainfall and surface runoff. The option price is higher than the water utility would want to pay on a regular, ongoing basis. Most of the time, the farmers continue to use their water. In addition to purchasing the option contract from farmers, the water utility buys insurance to protect itself against drought, that is, low water supplies in the upstream reservoir. The insurance contract is written so that payment is triggered when reservoir inflows hit an index level. This payment from the insurer provides the funds to exercise the option contract with farmers, and thus purchase the extra water needed during the drought. The reservoir insurance contract may be written so that payment to the water utility increases as inflows to the reservoir decrease, up to some maximum. But if you were the insurance underwriter, that is, the seller of the insurance here, what would you be concerned about in this contract? Can you think what you'd be worried about? Well, if I was writing a reservoir insurance policy, I'd think hard about the index to be used to establish when payment would occur. What would be desirable qualities of an index for triggering payment to the water utility? First, I'd want an index that was objective and easily measured. Second, I'd want an index that was independently verifiable. Third, I'd want to make sure that it was not under the control or could be influenced by the water utility. And finally, the index should be closely related to the losses incurred by the water utility. The table on this next slide is intentionally blank. It shows two options a water utility could use to tackle the problem of drought, perhaps exacerbated by climate change. The table on this slide is intentionally blank. It shows two options a water utility could use to tackle the problem of drought, perhaps exacerbated by climate change. The first option is to expand the infrastructure capacity of the water supply system. The second is to purchase a dry year options policy coupled with an insurance policy. Take a minute and think about how you would compare the pros and cons of these two options if you were the manager of the water utility. We think that the main attraction of the dry year options contract plus reservoir insurance to the water utility manager is that it could be much cheaper than spending more money for infrastructure. This would enable the utility to keep its rates down for its customers. Another attraction of the dry year options contract plus reservoir insurance is that it can be arranged quickly, without the political struggles that often accompany new infrastructure investment. On the other hand, the dry year options contract plus reservoir insurance does carry some risks. Would it be enforceable when a drought occurred and the utility needed the additional water from farmers? Would the insurance company actually pay the promised amount when the index was triggered? And would the public accept the logic of the dry year options contract plus reservoir insurance? Or would the public prefer the apparent certainty of new infrastructure? These are the kinds of difficult issues that water utility managers will face when designing financial adaptation tools in a world of climate change. If you'd like to learn more about the dry year options contract plus reservoir insurance, you can look at this 2012 paper by Scott Steinschneider and Casey Brown in the journal Water Resources Research. Now, to wrap up our discussion of the effects of climate change on water utilities, we think it's useful to think about how Professor Michael Hanneman of Arizona State University has compared living with climate change to having chronic disease. You still have to do all the things that needed to be done before, but everything becomes harder. This analogy seems especially apt for water utilities and climate change. Everything becomes a little harder, more complex, and more expensive. Thanks for watching this video.